Okay, let's unpack this. Imagine a world where your smartwatch, your continuous glucose monitor, your fitness tracker, maybe even your digital keys, they just never, ever run out of battery.
Mm.
What if that constant, nagging search for a charger, that little bit of anxiety when your device goes dead, what if it simply vanished?
Yeah.
What if your own body, your very own biology, could actually power these devices and securely transfer data, all without wires, no Wi-Fi needed, no constant
I mean, it
charging?
sounds like the future, doesn't it? But it's closer than we think.
It really does sound like something straight out of science fiction, a
Yes.
futuristic vision of, like, truly integrated tech.
Yeah.
What we're about to dive into today suggests it's, well, far closer to reality than you might think.
What's truly fascinating here, I think, is how researchers are fundamentally transforming our understanding of wearable technology.
Oh.
They're turning the human body itself into a dynamic power source and a secure communication channel.
Wow, the body itself.
Yeah, we're talking about a significant leap towards truly batteryless perpetual wearable operation. It's a paradigm shift, really. Moving from devices that are just powered on the body to devices intelligently powered by the body.
That's a big difference.
Huge. And this isn't just about convenience, it's about enabling a whole new class of always-on, almost invisible technology.
That's an incredible vision. So today, we're diving in to uncover how this groundbreaking technology works, why it's not just like an improvement, but a genuine game changer, and, importantly, what it means for your future interactions with the tech that lives on and around you.
Mm-hmm.
And this incredible, really cutting-edge work comes to us from a team of brilliant researchers at Purdue University, led by Nirmoy Modak and Shreya Sen.
And our deep dive today is primarily built on their detailed research paper. It's titled EQS Res HSBC, a 65-millimeter electroquasistatic resonant 5240 WeW human whole body powering and 2.19 WeW communications SOSO with automatic maximum resonant power tracking.
Okay, that's a mouthful. So.
Right. So SOO stands for System on Chip. It means the entire complex system, all the brains and the power stuff, is packed onto a single tiny piece of silicon.
Tiny chip, big title.
Exactly. And we've meticulously pulled out the most important nuggets of knowledge from this incredibly dense and innovative work. Our goal is to give you the shortcut to being well-informed about this quiet revolution that's happening.
So we've hinted at this futuristic vision, this batteryless world. But let's take a step back and understand why. Why is this kind of innovation so urgently needed right now? Why even talk about powering devices with our bodies instead of just plugging them in?
It truly boils down to, well, the Achilles heel of modern portable electronics. The battery. It's always the battery, isn't it?
Always.
For almost all wearable tech, especially in mission-critical applications like connected healthcare, think about continuous physiological signal monitoring for things like heart disease or diabetes.
Right, things you need working all the time.
Precisely. Or even secure authentication, where your wearable acts as a digital key. The ideal, the dream really, is perpetual batteryless operation. We just want these devices to work all the time, giving us uninterrupted data without us having to constantly worry about charging them.
That daily charging ritual.
Exactly. And while today's wearables are incredibly low power, they still need external charging. Or they might rely on ambient sources like tiny solar cells or kinetic energy harvesting.
Yeah, I've seen watches that charge from movement.
Right, but those ambient sources are often unreliable, or they're simply not powerful enough for long-term uninterrupted use, especially if you need to send power over longer distances across the body. Imagine a smart patch monitoring vital signs on your chest. It needs to be always on, always connected, always powered.
Can't rely on sunlight under your shirt.
Not reliably, no. So the goal is truly maintenance-free tech, always on, always connected, always working quietly in the background of your life.
Okay, so the need is clear. But what about existing methods for wireless power and data? Don't we already have ways to do this? It seems like they all fall short somehow, especially for this perpetual whole-body idea.
They do. Take traditional wireless technologies, for instance, things we use every day.
Like Bluetooth.
Exactly. Bluetooth, ANT, Zigbee. They're fantastic for many things, connecting your phone to headphones or your fitness tracker. But for this truly integrated batteryless future, they have some significant drawbacks.
Such as?
Well, first, they tend to be relatively power hungry compared to the tiny microwatt budgets we're talking about for perpetual operation. That just drains batteries faster, defeating the purpose.
Right.
But maybe more critically, their signals are broadcast through the air, they radiate outwards, and can easily leak into the surrounding environment.
Meaning anyone nearby could potentially pick them up.
Potentially, yes. And for sensitive data like medical information or unique biometric identifiers or, say, authentication credentials for secure access, this raises really serious security and privacy concerns.
I hadn't thought about that security angle as much.
It's a big one. And this is where the human body offers a unique advantage. Using the body itself as the channel helps confine the signal, making it much harder to intercept from the outside.
Okay, so beyond Bluetooth, what else is out there?
Well, you have other wireless power approaches. Consider RF energy harvesting, trying to capture energy from ambient radio waves like Wi-Fi or TV signals that are just floating around us.
Free energy, sounds good.
Sounds good, but the problem is it suffers from incredibly high signal loss when you try to use the body as a medium. We're talking about 40 to 60 decibels of loss for body channel lengths greater than, say, 40 centimeters.
Okay, translate 40 to 60 decibels for me. How bad is that?
It's really bad. A loss of 30 decibels means only 1,000th of the original power makes it through. 60 decibels, that's 1,000,000th.
Wow. Okay, so barely anything gets through.
Practically nothing over those distances. It's like trying to listen to a whisper from across a football field during a noisy game. On top of that, the human body itself casts an RF shadow. It absorbs and reflects radio waves, which degrades the efficiency even further.
So RF harvesting is pretty much a non-starter for this. What about wireless charging pads? Inductive links?
Right, inductive links. We use them for our phones. They can deliver decent power, sure, but they have strict alignment issues. You have to place your device just so.
Yeah, finding that sweet spot.
Exactly. Often needs physical contact, precise orientation, and they're inherently limited to very short distances. We're talking millimeters typically. Even improvements like integrating them into electronic textiles, embedding the node, still confine the receiver to a specific fixed position on the body. It's far from a flexible whole body solution.
Okay, so inductive is too short range and fiddly. What else?
We also see conventional energy harvesting techniques. Things like piezoelectric generators, they capture energy from movement or vibration. Or triboelectric generators, which get energy from friction, like rubbing materials together.
Like shuffling your feet on the carpet.
Kind of like that, yeah, but on a tiny scale. The issue is, these are highly constrained. Piezo devices often need to be placed at joints, like your knee or elbow, or maybe under your foot, where there's significant repetitive mechanical stress.
Makes sense.
Triboelectric generators also need specific mechanical interactions, and photovoltaics' tiny solar panels, well, they only work if the sensor has direct access to sunlight. That's often not the case for a wearable, hidden under clothes, or embedded in a shoe.
Right, so they're limited by where on the body they are, what you're doing.
Exactly. They're geographically or physically limited. You can't rely on them to power a sensor, say, on your torso all day long, regardless of activity or clothing. It prevents whole body continuous application.
Okay, so it seems like we're running out of conventional options here. Were there earlier attempts to use the body itself for power?
Yes, absolutely, and it's important to acknowledge those. There were previous attempts at what's called body-coupled power transmission. Some earlier work, like the research mentioned as reference 5 in the paper, was definitely a step in the right direction. They tried using the body to conduct power, but it just wasn't suitable for longer channels. Think 60 to 100 centimeters, like trying to power a sensor on your ankle from a device maybe worn on your shoulder.
Yeah, that's a long way electrically.
It is.
Yeah.
And the efficiency just plummeted. It dropped below a dismal 1% over those distances. Plus, and this is critical, some of those early methods delivered power levels that, while trying to get enough energy across, could actually exceed the safety limits set by organizations like IE.
Oh, that's not good.
Yeah.
Safety first.
Absolutely. So while the basic idea of using the body was there, the practical implementation for a truly safe, efficient, whole-body solution remained elusive. And this really sets the crucial context for the innovation we're discussing today. It directly addresses these long-standing limitations.
This really highlights the core problem, doesn't it? But what if we could flip that, turn those limitations into advantages? What if your own body wasn't just wearing the tech, but was the tech's medium? This is where it gets really interesting, right? Human body communication, HBC, and this body-coupled power transfer idea.
Indeed. HPC has emerged as a significantly more power efficient and, importantly, inherently more secure alternative to traditional wireless communication.
How so?
Well, instead of broadcasting signals through the air where they dissipate rapidly and can be easily intercepted, HBC utilizes the body's natural electrical conductivity. It basically confines the signal within close proximity to the human body.
Like an invisible wire following your skin.
That's a good way to think about it. This dramatically reduces the power required to send a signal across a given distance. And crucially, it enhances security because the signal is much harder to pick up from outside the body. It's like having a private, invisible data network that exists only around you, powered by you.
Okay, that's the communication part. What about the power?
Right. The more recent advancement, and really the core of this research, is extending this concept beyond just communication to include robust power transfer through the human body, what they call body-coupled power transfer.
But you said earlier attempts struggled with distance and efficiency.
Exactly. That was the major hurdle. The received power became incredibly inefficient and just unsustainable for channel lengths greater than about 40 centimeters. You can maybe power a device on your wrist from another, on your bicep, okay, but not reliably from your waist to your ankle or your chest to your foot.
So the 40-centimeter limit was a real barrier.
It was a huge barrier, and this is the crucial problem the Purdue research team specifically set out to solve.
So the big leap here, the breakthrough, is making this HPC work efficiently for both power and data across the entire body seamlessly, regardless of the distance between devices or even your posture. What does this research, this EQS Res HPC, specifically aim to achieve?
Okay, so the core contribution of this work is leveraging a really sophisticated approach. They use what's called electroquasistatic resonant HBC, or EQS Res HBC, and they combine it with an intelligent mechanism called maximum resonant power tracking, or MRPT.
Electroquasistatic resonant HPC with MRPT.
Got it. Right, this powerful combination enables channel length independent whole body communication and powering.
Channel length independent, meaning the distance doesn't matter as much.
Exactly. It means the efficiency of power or data transfer doesn't drastically degrade whether the devices are 10 centimeters apart or 100 centimeters apart on your body, or if you're standing, sitting, or moving around. This is groundbreaking because it's the first system ever designed to simultaneously transfer both power and data from a battery-operated central device, they call it a hub, to a completely batteryless, energy-harvested wearable device, the Node-D.
Hub powers the node through the body.
Precisely. The ultimate goal, and what this research really makes a reality, is truly perpetual, maintenance-free, batteryless operation for wearables operating all around and on your entire body.
That's the grand vision, a truly invisible network powered by, well, you. But to really appreciate this leap, we need to peel back a layer. Understand the science behind how our body becomes this incredible channel. So electroquasistatic, it still sounds like a mouthful. What does it actually mean for us in this technology?
You're right, it's a technical term, but the underlying concept is quite elegant, and it's critical to why this works so well. Electroquasistatic, or EQS operation, is fundamentally different from traditional radio frequency, or RF, approaches.
How is it different?
In an EQS system, the electric field changes slowly enough relative to the wavelength that at any given instant you can consider it almost static, like the field around a charged object that isn't changing.
Okay. Slow changes. Why is that important?
It's key because it allows for a far more uniform power delivery throughout the entire body. Unlike RF-based methods, where signals act like waves, propagating outwards and quickly attenuate, losing efficiency over distance.
In like that 60 dB loss you mentioned.
Exactly. EQS prevents that severe efficiency degradation as the channel length increases.
So it's less like broadcasting a signal and more like...
What? Think of it more like using the body itself as a kind of electrical conduit or waveguide. The electric field lines are primarily confined to the close proximity of the body. It's less like water splashing everywhere from a hose and more like water flowing contained within a pipe.
Oh, okay. That helps.
The researchers use sophisticated simulations called finite element method, or FEM simulations, to visualize this. Figure 1 in their paper shows it quite vividly. You see how the power is available consistently throughout the body model.
And that confinement helps security too, right?
Absolutely. That confinement not only dramatically improves efficiency, but as we touched on, it significantly enhances security. Because the signal isn't radiating far out, it's much harder for unauthorized receivers to intercept from outside your personal space. It's like a signal that sticks to you.
Okay, so EQS is the foundation. But how does the body itself interact with these signals? What's happening at that biophysical level when you attach a device?
This is where the biophysical model becomes critical. It's like the electrical blueprint for the human body channel. The core setup, which is shown nicely in Figure 2 of the paper, involves a transceiver system that's a device that can both transmit and receive.
Like the hub or the node?
Exactly. It's capacitively connected to the human body. Usually, this connection is made via metallic dry electrodes, the kind you might see on an ECG sensor or a fitness tracker.
Okay.
The positive electrodes of both the transmitter and receiver are placed on the body's surface. The negative electrodes are typically left electrically floating, not connected to anything specific. This setup creates a specific electrical circuit path through and around the bottle.
And electrically, what does the body look like in this circuit?
That's where the lumped elements come in. We can model the electrical behavior using a series of tiny capacitors that represent how the body and electrodes store charge. There's CP and CL, they call these plate capacitors at the transmitter TX and receiver RX. These represent the capacitance directly between the electrode and the body tissue underneath. They're typically small, around 10 to 30 picofarads.
Pico. It's tiny, right? Trillions.
Brilliance of a farad, yes, very
Yeah.
small. Then you have CRET TX and CRET RX. These are the return path capacitances. These model the path the electrical current takes from the floating negative electrodes back to earth ground, usually through the air or surrounding objects. These are even smaller, typically less than 1 picofarad each.
Okay.
And finally, there's C-body. This represents the capacitance between the entire human body itself and earth ground. It's much larger, usually around 100 to 200 picofarads, because our whole body acts like a capacitor relative to the environment.
Wow. Okay, so lots of tiny capacitors modeling the connection. What's the tricky part?
The crucial point here, the thing that creates both the challenge and the opportunity, is that these parameters, especially those tiny return path capacitances, are not static. They're highly dynamic.
Because we move.
Exactly. They change constantly with your movement, your body posture, what you're wearing, even the environment around you, like how close you are to a grounded metal desk or a wall.
I see.
This variability is a huge hurdle. Any robust whole-body communication and powering system must overcome it, because these changing capacitances directly affect how efficiently power and data can be transferred. They change the tuning of the body channel, so to speak.
Now, this is where they really crank up the performance and deal with that variability, right? They're
Mhm.
not just using EQS, they add resonance into the mix. Resonance sounds like tuning forks or something. Why is that such a game changer here?
Resonance is absolutely the magic ingredient, and your tuning fork analogy isn't far off. In electrical terms, resonance happens when you combine capacitors, which store energy in electric fields, and inductors, which store energy in magnetic fields, in a circuit. At a specific frequency, the resonant frequency their opposing effects cancel out, allowing energy to oscillate back and forth very efficiently.
Okay.
It dramatically increases either the current or the voltage in the circuit at that specific frequency. By carefully adding inductive coils, which are essentially tiny coils of wire to this capacitive human body channel, they create these highly efficient resonant circuits.
Tuning the body channel electrically.
Precisely. This dramatically boosts either power transfer or communication efficiency by leveraging this inductive cancellation effect. The Q factor, or quality factor, is key here. It's a measure of how good the resonant circuit is, how much energy it stores versus how much it loses each cycle. A higher Q means much more efficient energy transfer or clearer communication with less energy wasted.
And they use resonance differently for power versus data, you mentioned.
Yes, and this is really clever. They employ two distinct resonance strategies, each optimized for a different job. First, for power transfer, where the goal is simply to get as much energy as possible into the NODU device to charge it up, they use EQS series resonant HBC.
Series resonance for power. Why series?
Okay, so the maximum received power depends on the square of the received voltage, but the transmitted voltage, VTX, is limited by the chip's technology, basically, the supply voltage you can safely use.
Can't just crank up the voltage indefinitely on the chip.
Right. So to get around this limit and deliver substantially more power, they put an inductor in series with the body capacitance at the transmitter. At resonance, this series arrangement acts like a voltage multiplier. It increases the voltage across that plate capacitor CP by a factor of Q.
So the voltage on the body gets boosted by Q.
Effectively, yes, the driving voltage is boosted. This leads to the available power increasing by Q squared, Q2, at the transmitter. Then, if you also add a parallel inductor at the receiver to match the circuit optimally, the received voltage gets boosted by another factor of Q.
Wait, so Q squared at the transmitter times another Q at the receiver.
Exactly. The overall received power capability increases by a staggering factor of Q to the power of 4.
Q to the fourth. That's huge.
It's an enormous boost. This isn't just a small improvement, it's an exponential leap. It makes continuous, reliable charging possible for these tiny wearables in a way that was just unimaginable before. It takes them from often dead to potentially always on. Figure 3b in the paper shows this configuration optimized for just injecting maximum power.
Wow. Okay, so series resonance is about getting as much raw juice, as much power into the body as possible, cranking it up exponentially.
Exactly. It's all about maximizing the peak power transfer for charging up those batteryless NODs. Now, for data communication, the goal shifts. It's not about brute force power. It's about efficiency and signal clarity. Here, they switch to EQS parallel resonant HBC.
Parallel resonance for data. How does that work?
Here, the key metric is the figure of merit, or foam. It's basically the ratio of received voltage, the signal strength, to the transmitted power, how much energy it costs to send. You want a high foam, a strong signal for very little power cost.
Makes sense for data. Be efficient.
Precisely. To get a higher foam, you need to reduce power loss at the transmitter. Parallel resonance does this beautifully. They place an inductor in parallel with that plate capacitor CP at the transmitter.
Okay, parallel this time.
Right. At resonance, this parallel arrangement cleverly reduces the current the transmitter needs to supply by a factor of Q, without changing the transmitted voltage significantly. Less current means less power consumed.
Ah, P equals I2R, so less current, less power.
You got it. This decreases the overall power consumption by Q squared, Q2, which directly increases the F-ohm by Q2. Now, if you also add a parallel inductor at the receiver, it further boosts the received signal voltage by Q, making the overall F-ohm cubed Q3 times higher than regular non-resonant EQS HBC.
Q cubed better signal for the power. That's also amazing.
It really is. So think about getting crystal clear sensor readings, maybe heart rate data, from a device on your ankle reliably sent to your wrist without draining significant power even while you're moving around. That's the level of efficiency this provides for data. Figure 3C shows this parallel setup, optimized for signal integrity with minimal power burn.
So, if I'm getting this right, parallel resonance is about being super efficient with data, using minimal power to ensure those signals are crystal clear across the body, even for complex info. That's really smart, having two different strategies.
Exactly. It's about optimizing for signal clarity and ultra-low power consumption for the data part, rather than just raw power delivery for the charging part.
But why have two? Why not just pick one?
That's a great question. The paper, especially looking at figure 4, explicitly makes the case. Series resonance is demonstrably the best for peak power transfer, getting the most watts across, while parallel resonance is the clear winner for voltage mode communication because it gives that much higher figure of merit for data efficiency. They are optimized for different things.
Okay.
And this strategic choice also has a big impact on the requirements for the driver circuits, the electronics, that actually push the signal into the body.
How so?
For series resonance, to get that high power, you need high current. This means the transmitter's internal resistance, its source resistance, RS, needs to be much lower than the effective resistance of the inductor and load, RL. Low resistance allows high current flow.
Okay. Strong driver for power.
Right. But for parallel resonance, the condition is relaxed. Because the transmitter current is minimized at parallel resonance, the source resistance, RS, can be higher. It still needs to be relatively low, but the requirement is RS should be much less than Q2 times RL. This means you can actually use a weaker driver circuit for data communication, one that consumes less current and therefore less power compared to the beefy driver needed for series power transfer.
Ah, so they even optimize the driver circuits for each mode.
Absolutely. This careful distinction and optimization of the drivers is key to the system's overall efficiency and its ability to switch seamlessly between delivering power and sending data.
Okay, so resonance is incredibly powerful, boosting efficiency like crazy. But you mentioned earlier the human body isn't static. We move, our posture changes, the environment changes. All those capacitances shift around. How do they keep this delicate resonance thing working? How do they stay perfectly in tune?
You've hit on maybe the most critical challenge, and honestly, the solution is why this technology is so practical. That resonant frequency, FECAR, is highly sensitive to several parameters in that biophysical model, especially the plate capacitor CP and that tricky return path capacitance,
Yeah.
TX.
Right, the ones that change.
Exactly. CP is mostly determined by the device's physical size, bigger device, bigger CP, which shifts Freet. But crit TX is the real dynamic variable. It's that capacitance between the electrode's ground and the earth ground, and its value changes significantly with body posture, with body shadowing effects, how close you are to a grounded object, even the size of the device's own ground plane affects it. Figure 5 in the paper shows these dependencies quite clearly.
So it's constantly changing.
Constantly. The key insight is its time-variant nature. The resonant frequency 4 changes every time a person moves or changes their environment. If the system's operating frequency drifts even slightly away from the perfect resonance point, poof! All those fantastic efficiency and power benefits we just talked about, they vanish.
It's like trying to tune an old radio that keeps drifting off the station.
Exactly like that. You lose the signal, or in this case, you lose the efficiency. This makes real-time, on-the-go resonance frequency tracking not just a nice-to-have, but absolutely essential for the system to work efficiently and consistently in the real world.
So how do they track it? How do they stay tuned?
This is where the maximum resonant power tracking, or MRPT, mechanism comes in. It's a truly ingenious feedback loop, shown in Figure 6. It's the intelligence inside the hubby that ensures the system always operates at the optimal frequency, whatever that frequency happens to be at that exact moment.
Okay, how does MRPT work?
It works in a continuous cycle with two main phases. First, there's the scan phase. The HOB systematically changes its transmission frequency, sweeping from a preset lower limit to an upper limit, taking small, discrete steps. While it's doing this sweep, it's constantly listening to the body, measuring the electrical potential on the body surface using that feedback unit we'll discuss later.
Listening for what?
It's listening for the peak. The body potential will naturally reach its maximum value when the system's frequency hits the perfect resonance frequency for the current body conditions. It's like finding the loudest point on that drifting radio dial. Then comes the detection phase. The system intelligently identifies this peak in the measured body potential. That peak tells it the exact resonant frequency right now.
Found it. Then what?
Then it enters the transmission phase. The hub B locks onto that detected resonant frequency, FR, and all subsequent power transfer, using series resonance, or data transfer, using parallel resonance, happens precisely at this optimal frequency. This maximizes the efficiency and minimizes energy waste until the next scan cycle needs to run to check if things have changed.
So it's constantly, maybe not constantly, but regularly. Scanning, listening to the body, finding that sweet spot frequency, locking on, transmitting, and then maybe scanning again later, like an adaptive radio station built just for your tech, always tuning itself.
That's a perfect analogy. It's a closed-loop adaptive system. It seamlessly adjusts to the dynamic nature of the human body channel, ensuring those huge benefits of resonance are maintained under real-world, constantly changing conditions. Without MRPT, honestly, the system's performance would degrade so quickly it would be impractical for everyday use. #tag the architecture of a batteryless future system design.
That adaptability is absolutely key. So with this smart frequency tracking and the two different resonance tricks for power and data, we're clearly moving beyond just one device getting power. This sounds like a cornerstone for a whole network of devices interacting across the body.
Yeah.
What's the bigger picture here? What are the researchers building towards?
The larger vision, the ultimate goal, is what's often called the futuristic Internet of Body, or IOB. Reference 23 in the paper talks about this. Imagine a world where all your personal electronic devices, whether they're worn on your skin, maybe embedded in your clothes, or even potentially implanted within the body someday.
Wow, implants too.
Potentially, yes. Imagine all these devices seamlessly connecting, communicating, and operating together, all powered and networked by your body itself. This research provides a fundamental building block for that IOB vision. It enables devices to be truly batteryless and perpetually operational across and potentially within the human body.
So it moves us beyond just wearables.
Exactly. Towards invisibles. Technology that's always there, always on, but never intrusive. It doesn't demand your attention for charging or require conscious effort to connect things. It just works, integrated into you.
Okay, so how is the system structured to enable this IOB vision? What are the main parts?
To realize this, the system is designed with two primary components, which you can see laid out in Figure 7 and Figure 8. First, there's the hubba. This is typically a slightly larger device, and it's battery-operated itself, at least for now. It acts as the initiator, the power and data master.
Central controller.
Right. It's responsible for transmitting the energy and data out, and also for receiving data back from other devices. Think of it as the conductor of this body-based orchestra. Second, there's the NOD, and this is the truly revolutionary part. The Node is a batteryless, energy-harvested wearable device.
Completely batteryless.
Completely. It receives its operating power and any necessary data from the hub transmitted through your body, and it can also transmit its own data, say, sensor readings, back to the hub using the same body channel. This is where the perpetual operation really happens because the node never needs its own traditional battery or any external charging. It literally lives off the energy harvested from the hub via your body.
Okay, hub and node. How do they coordinate? How do they know when to send power versus data or when the node should talk back?
They coordinate using carefully timed operational phases. They use a technique called time division multiple access, or TDMA. Basically, they take turns using the body channel.
Like time sharing.
Exactly. There are three distinct phases in their protocol. Phase 1. The hub transfers power to the node. This uses that high-efficiency series resonance strategy we talk about to maximize energy delivery.
Charge up the node.
Right. Then, phase 2. The hub transfers data to the node. Now it switches to parallel resonance for efficient low-power voltage mode communication, maybe sending configuration data or commands.
Hub talks to node.
Correct. Finally, phase 3. The node transfers its data back to the hub. It also uses parallel resonance for this transmission, again optimizing for low power efficiency since the node is running purely off harvested energy.
Node talks back to hub, power, hub to node data, node to hub data.
Got it. And synchronization between the hub and node is absolutely critical for this to work without signals colliding. A precise timer within the hub manages the exact timing and duration of these three phases. And there's a sophisticated digital control logic unit called a finite state machine, or FSM, in the node that ensures it operates in perfect sync with the hub's schedule.
So the hubby says power time, then my turn to talk, and then your turn to talk.
In essence, yes. This carefully choreographed sequence ensures devices aren't trying to send and receive simultaneously, optimizing both power and data transfer without interference, all while the MRPT is working in the background to keep things tuned to the body's dynamics.
It really is like a finely choreographed dance then, isn't it? Each device knows its steps, knows when to lead and when to follow, all orchestrated through your body by the hubby. And to make this dance possible, there must be some incredibly smart and efficient circuit blocks inside that tiny chip.
Absolutely. The researchers designed a whole suite of intelligent circuit blocks to make this adaptive, ultra-low power operation a reality. Let's maybe walk through some of the key ones.
Yeah, let's get into the hardware details. What's under the hood?
Okay, first, at the heart of the hub, you have the synthesizable control unit. Think of this as the digital brain. It orchestrates everything. It initiates the operations, manages that frequency scan for the MRPT, sweeping from low to high frequency in discrete steps, and it makes the crucial decisions based on the body potential feedback to lock onto the correct resonance frequency.
So it runs the MRPT.
Yes, and it controls the TDMA phases. It's also highly flexible.
Yeah.
The paper mentions it's user configurable, so you can adjust things like the scan resolution, the frequency limits, the duration of each power or data phase. This programmability means the system can be adapted for different applications, maybe powering a very low power sensor versus transmitting more complex data.
Okay, the brain. What else?
Next, crucial for any ultra-low power system is the on-chip clock generator. You need precise timing, but you need it using minimal energy. They implemented a 3-stage current-starved ring oscillator. You can see the diagram in Figure 9.
Current-starved. Sounds painful.
It just means it's designed to use very little electrical current. It's a highly optimized, digitally controlled heartbeat for the chip. It can generate a wide range of frequencies, from a slow 100 kilohertz up to a pretty fast 5.1 megahertz, even running at a very low 0.6 volt supply. Vary. And it includes a duty cycle corrector to ensure a stable 50% duty cycle clock, which is important for reliable digital operations. During that initial scan phase, the hub's control unit dynamically tunes this oscillator's frequency to find the resonance point. Once resonance is detected, the clock frequency is locked, and the whole system operates optimally at that frequency, sipping power.
Got it. Brains, heartbeat. What sends the actual signal?
That would be the fully synthesizable transmitter. This block, shown in Figure 10, is what actually sends the data and power signals out into the body channel. It uses a very simple and low-power modulation scheme called on-off keying, or...
Okay, on-off keying, like Morse code.
Exactly like Morse code, basically. You represent digital data by simply turning the carrier signal on or off. It's simple and very power efficient. For generating that carrier signal itself, it uses direct digital synthesis, or DDS, which is a way to create accurate variable frequency digital waveforms.
And it handles both power and data.
Yes, and importantly, it has separate output ports that are optimized for each function. There's a signal port designed for data communication, leveraging parallel resonance for that ultra-low power operation. And there's a power port for power transfer, using series resonance to deliver the maximum peak power. The transmitter also supports user-defined modes like scan, transmit, and wait, making it really flexible for orchestrating those TDMA sequences.
Okay, transmitter's ready. But actually driving the signal into the body must be tough, right? You said the body is like a capacitor.
It is tough, and you've hit on a critical design challenge. The communication and powering buffers. These are the amplifier circuits that take the tiny electrical signals generated on the ship and actually drive them into the much larger, more complex capacitive load presented by the human body.
Heavy lifters.
Exactly. And the paper points out they consume almost 90% of the total power used during transmission.
90%, wow.
Yeah, it's a huge chunk. The challenge is incredibly delicate. If your buffer is too weak, it simply can't drive the body capacitance effectively. You won't get enough signal swing, enough voltage for reliable transfer. But if you make the buffer too strong, overly powerful, it wastes a ton of power, mainly through leakage currents when it's not actively switching.
A balancing act.
A very fine balancing act. To nail this, the researchers designed highly optimized chains of inverters. Think of them as stages of amplification. They use a chain of 6 stages for the power transfer buffer and 4 stages for the data communication buffer. Each successive inverter in the chain has an incrementally increasing driving capability, carefully sized and tuned.
Tailored for each job.
Precisely. Tailored to meet the specific electrical requirements for both series resonance, where you need low resistance for high current, and parallel resonance, where the resistance requirement is relaxed for high voltage efficiency. This meticulous buffer optimization is absolutely key to achieving their impressive overall power efficiency numbers, despite the inherent difficulty of driving the human body.
Okay, so the who sends the signal. How does it listen for that resonance peak during the scan? What's the ear?
That's the job of the feedback unit, also called the resonance sensing mechanism. Figure 11 details this. It starts with a critical safety feature, a capacitive voltage divider.
Why divider?
Because, as we discussed, the body potential can reach up to tens of volts at resonance, especially in ideal conditions. That's far too high to feed directly into the delicate, low-voltage circuits on the 65-nanometer chip. It would fry it instantly.
Right, you need to step it down.
Exactly. So they use an on-chip 5 picofarad capacitor combined with a tiny off-chip capacitor, either 50 or 100 femtofarads. Femto is even smaller than pico, 1,000 times smaller. This divider safely attenuates or reduces the high body potential by 50 to 100 times, bringing it down into a safe range, typically below 100 millivolts, before it reaches the chip's input.
Okay, safe voltage now. Then what?
This attenuated AC signal then goes into an envelope detector, or ED. You can think of an ED as a specialized filter. It strips away the high-frequency carrier signal and outputs just the slowly varying amplitude or envelope of the signal. This envelope voltage will naturally peak precisely when the input frequency hits resonance.
So the ED output traces the peak. How is the peak found?
To pinpoint that peak, they use a clever circuit, a successive voltage level comparator equipped with a strong arm latch. This comparator continuously compares the output voltage of the ED from one scan frequency step to the next.
Comparing consecutive measurements.
Right. As the scan frequency sweeps up towards resonance, the ED output voltage increases, so the comparator output a logic high. As soon as the frequency passes the resonance peak, the ED output starts to decrease. The comparator detects this drop and switches its output to a logic low.
So it goes high, 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 then low when the peak is passed.
Exactly.
Yeah.
That transition from high to low tells the control unit, we just passed the peak. The previous frequency step was the resonant frequency. This single sampler sensing scheme, as they call it, is incredibly energy efficient. It avoids needing power-hungry analog-to-digital converters, ADCs. And it's designed to be robust, rejecting false glitches and noise, ensuring accurate resonance detection. The hub is very sensitive, very efficient ear.
Neat. Very clever. Are there other power-saving tricks in the architecture?
Yes, another important one is the synthesizable adaptive clock divider. Think about it. While the transmitter needs to operate at that potentially high resonance frequency, around 1 megahertz maybe, most of the other support components in the hub, like the main control unit, memory access, etc., don't need to run nearly that fast.
They can run slower.
Much slower. This adaptive clock divider allows these less critical blocks to operate at frequencies that are 100 to even 1,000 times lower than the main resonance clock. This significantly cuts down the overall power consumption of the hub.
Smart. Does it do anything else?
It does. It also solves a subtle but important problem during the MRPT scan phase. If each scan frequency step were transmitted for an equal number of clock cycles, then as the frequency increased, the actual time duration spent at each step would decrease. This could cause problems for the envelope detector, not giving it enough time to settle accurately at higher frequencies.
Need consistent measurement time.
Exactly. So the adaptive clock divider cleverly ensures an equal time duration for each scan frequency step by linearly incrementing the number of clock cycles per step as the scan frequency increases. It keeps the measurement window consistent. It also generates the necessary non-overlapping clock signals needed for the feedback loop components, as shown in Figure 11, ensuring perfect timing coordination within the resonance tracking system.
Okay, that covers the hub's intelligence and power handling. What about the no DE, the batteryless part? How does it survive?
The Node's lifeline is its energy harvester. This is what truly enables its batteryless perpetual operation. It's a highly efficient circuit, detailed in Figure 12, consisting of 30 stages using what's called a sub-threshold multiplier topology.
30 stages. Sounds complex. What's its job?
Its job is to take the tiny amount of AC power received from the HUT-G, remember. After potentially 60 decibels of loss through the body channel, this might only be in the range of tens of millivolts peak to peak.
Right. Very little power arriving.
Very little. The harvester's job is to efficiently convert this weak AC input into a stable, usable 1-volt DC voltage. This DC voltage is then stored in a moderately sized off-chip capacitor, about 40 microfarads, which acts like a tiny rechargeable battery or energy reservoir for the Node.
And it can work with those tiny voltages.
Yes, it's highly sensitive. The paper states it can start operating with as little as 70 millivolts peak-to-peak AC input.
Okay, so it harvests the power. How long does it take to get going?
The measurements showed it takes about 14 seconds during that initial power transfer phase, phase 1, to charge up that 40 microfarad capacitor to the required 1 volt, basically bringing the node to life from a dead start.
14 seconds. And how long can the node run on that charge?
Well, the node's communication module is incredibly efficient. It consumes only about 2 microwatts when it's transmitting data back to the hub. But even so, that 40 microfarad storage capacitor can only sustain that communication for approximately 10 seconds before its voltage drops too low for the circuits to function correctly.
Only 10 seconds of talk time.
Right, which necessitates a duty-cycled operation at the node managed by its FSM. The system can't just transmit constantly. A typical cycle might be. The hub powers the node for, say, 15 seconds, phase 1, charging up the capacitor. Then the node uses that stored energy to communicate its collected data back for maybe 5 seconds, phase 3. Then the cycle repeats.
Charge, talk, charge, talk.
Exactly. It's an elegant dance of power harvesting and brief, efficient communication bursts that allows for continuous, sustained operation without ever needing a traditional battery in the node A.
Very clever. And finally, both the hub and node A need to receive signals, right?
Correct. They both need receivers, and the paper mentions they share identical receiver blocks for simplicity and efficiency. Each receiver consists of several stages. An analog front-end, AFE, to initially process the weak incoming signal, another envelope detector, ED, to extract the data envelope, a baseband amplifier to boost the signal strength, a sampler to digitize it, and finally, a sophisticated oversampling clock and data recovery, or CDR, unit.
CDR, what does that do?
The CDR is particularly intelligent. Its job is to lock onto the timing of the incoming data stream and extract both the clean data bits and a synchronized clock signal, even if the incoming signal has timing imperfections like jitter or glitches caused by noise in the body channel. It's crucial for reliable data reception.
And it's adaptable.
Very adaptable. It's configurable for data rates ranging from 50 kilobits per second all the way up to 1 megabit per second. It uses its own internal finite state machine, FSM, to adapt to the different data phases. Phase 2 for hub receiving, Phase 3 for node receiving, ensuring robust clock recovery and accurate data decoding. This ensures that communication is reliable, achieving that low bit error rate, BER, of 10 to 5. They reported only one mistake in 100,000 bits.
That's a truly complex and finely tuned architecture. Designing all that on paper with the theory sounds incredibly solid. But, the real test is how it performs in the real world. What did the actual measurements tell the researchers? Did it live up to the promise? Hashtag tag tag the proof in the performance measurement results and impact.
That's always the million-dollar question, isn't it? And the results here are genuinely compelling. They really do seem to push the boundaries of what's possible with body-coupled power and data.
So how did they test it?
Well, first, they actually fabricated the entire system, the EQS resonant HBC Hoja, and the batteryless node as a single integrated system on chip. They used a standard, efficient semiconductor process called TSMC 65 nanometer low power CMOS technology.
65 nanometer. That's pretty small, right?
Very small. The entire active area for the chip, all those blocks we just discussed, occupies just 0.13 square millimeters. That's roughly the size of a single grain of sand.
Incredible, packing all that complexity into such a tiny space.
It really is. Now, to evaluate its real-world performance thoroughly, they measured key metrics like transmitted voltage, power delivered, received power, and overall efficiency across 3 distinct human body communication scenarios. These are shown in Figure 13 of the paper.
Why 3 different scenarios?
Because, as we discussed, that return path capacitance, how the body is rounded or not, changes drastically depending on the environment, and that change significantly impacts performance. So testing in different realistic setups is crucial.
Makes sense. So let's talk power transfer first. That Q to the 4th boost sounded amazing theoretically. Did it hold up?
It did, especially under the right conditions. The results for power transfer, which are summarized nicely in Figure 14, Parts 3E, show some really impressive figures.
Lay them on me. Scenario 1.
Okay, first, they tested a machine-machine interaction scenario. You can think of this as a sort of baseline, an ideal lab condition. It represents 2 devices interacting, maybe on a test bench, where both have a strong, stable connection to earth ground.
Like scientific equipment, well-grounded.
Exactly. In this ideal setup, they achieved an average of 240 microwatts of received power at the node E. That's a significant amount, easily enough to power many ultra-low power sensors continuously. And the efficiency was remarkable, 37% efficiency.
37% efficiency through the body. That's huge.
It is, and critically, in this specific well-grounded scenario, the power transfer actually became independent of the human body's specific parameters, because that variable return path capacitance was effectively taken out of the equation by the strong ground connection. They could also push the transmitted voltage to over 10 volts using just a 1.2 volt chip supply, thanks to resonance, delivering a peak transmitted power of 650 microwatts.
So this really proves the core tech works exceptionally well when grounding isn't the variable factor. It shows off that resonant boost.
Precisely. It validates the fundamental principle in a controlled environment. Now, let's get more realistic. Scenario 2 was the tabletop scenario. This is designed to mimic more common everyday interactions. Imagine small devices placed on a desk or table where a person might be sitting, maybe touching the devices or the table, providing an indirect ground path.
Okay, more like how we might actually use things. What happened here?
In this tabletop setup, they achieved 28 microwatts of received power with an efficiency of about 3%.
Okay, quite a drop from the machine-machine case.
Yes, a significant drop. Here, that return path capacitance, CRAT, was estimated to be in the range of 100 to 200 picofarads. This less ideal, more variable grounding significantly reduced the power that could be effectively transmitted compared to the pristine lab setup. Still, 28 microwatts is a non-trivial amount of power for a battery-less sensor. It's definitely usable.
Right, still enough to power something small, perhaps intermittently. And the third scenario, the ultimate goal.
Exactly. The third test was the wearable scenario. This represents the target application. Truly integrated health monitors, fitness trackers, authentication devices, where the hub and node are both worn directly on the body with no direct connection to earth ground at all, just body contact.
Not toughest case.
Arguably, yes. And here they measured 5 microwatts of received power. But interestingly, the efficiency was 7%.
Wait, 7%? That's higher efficiency than the tabletop scenario, even though the power is lower. How does that work?
It's counterintuitive, but it highlights the subtleties of the EQS HBC physics. In this fully wearable scenario, that return path capacitance CREAT was actually very, very small, estimated at only 0.5 to 1 picofarad. Because there's no easy path to ground, less energy leaks away from the body channel itself. This resulted in lower overall power loss within the body channel, leading to surprisingly better end-to-end efficiency compared to the tabletop case, even though the total transmitted power was lower due to the lack of grounding.
Wow. So the lack of ground actually helped efficiency in a way, even if it limited total power.
In this specific resonant EQS framework, yes. It demonstrates the system's inherent ability to adapt and operate efficiently even in these challenging, fully ungrounded wearable environments. And that's exactly what you need for this pervasive Internet of Bodies vision. 5 microwatts might sound tiny, but for ultra-low power sensors designed for this, especially operating in a duty-cycled manner, it's potentially enough.
Okay, so stepping back, how does this compare? What does this mean for all those previous attempts at body-coupled power you mentioned earlier? You hinted at some big numbers.
This is where the innovation really hits home. It's not just an incremental improvement, it's a leap. Compared to the best prior state-of-the-art methods for trying to send power over a long 100-centimeter body channel in that realistic tabletop scenario, this new EQS resonant HBC system achieves more than 25 times the amount of power transfer. And it does it with over 100 times higher efficiency.
25 times the power, 100 times the efficiency.
Yes. And specifically for that challenging long-channel wearable whole-body power transfer, think shoulder to ankle, it's 100 times more efficient and delivers more than 10 times the peak power compared to previous body-coupled ambient powering principles. Figure 20 in their paper lays out these comparisons clearly.
Those are genuinely monumental improvements.
They really are. These aren't just numbers. They fundamentally change the calculus. They shift perpetual batteryless wearables from being a theoretical concept, maybe possible in limited scenarios, to being a practical, achievable reality across the whole body. That dream of your health monitor just always working, always sending data, never needing a charge, it suddenly feels within reach because of gains like these.
Okay, the power transfer is clearly a game changer. But power is only half the story for many applications, right? Communication is just as vital, maybe even more so, for things like medical monitors or secure keys. How well did the system handle the data transfer part?
Right, data is crucial. And for data transfer, they switched to that parallel resonance strategy, optimized for efficiency and signal integrity, benefiting from that Q-cubed FUM boost. The measurements absolutely confirm its impressive efficiency.
How efficient?
The transmitter, when sending data, consumes only 2.19 microwatts. That's at a data rate of 20 kilobits per second while driving a typical 30 picofarad body load. You can see this in figure 14.
2.19 microwatts. That's incredibly low power.
It's tiny. And importantly, it represents a 33% lower power budget compared to what regular non-resonant EQS HBC would require for the same data rate and load. That's the direct benefit of the inductive cancellation from parallel resonance. To put it in perspective, the entire digital control unit and the clock generator in the hub only consume about 0.3 microwatts on average. It shows just how optimized the core communication circuitry is. It barely sips power.
And the receiver. Can it pick up weak signals reliably?
The receiver performance is also exceptional, as detailed in Figure 15, Parts A and B. It operates reliably at that very low bit error rate, BER, of 10 to 5 at the 20 kilobits data rate. Remember, that's only one bit wrong in every 100,000 bits, sent extremely reliable.
Yeah, that's accurate.
And it achieves this with a good timing margin, 0.56 UI unit interval, meaning it's robust against timing variations. It also boasts really high sensitivity. It can accurately detect signals as weak as negative 60 dBm, which corresponds to about 318 microvolts peak to peak when running at 1 kilobps. Even at the faster 20 kilobps rate, its sensitivity is negative 52 dBm, or about 794 microvolts.
So it can pick up very faint signals coming through the body.
Exactly. And maybe most impressively, in its lowest power standby or operational mode, the entire receiver consumes only a minuscule 72 nanowatts.
72 nanowatts. That's almost nothing.
It's incredibly low power. This ultra-low power consumption for both transmission and reception is what truly enables that batteryless no-D to function effectively. It can wake up, listen for commands, collect sensor data, transmit it back, and do it all reliably while running purely off that tiny bit of harvested energy.
Okay, the numbers are staggering.
Yeah.
25x power, 100x efficiency, microwatt communication, nanowatt reception. But it's still a bit abstract. What does this actually look like when it's working? Did they show it in action reacting to a person moving?
They did, and these real-world demonstrations are crucial for showing practicality. Figure 16 and Figure 17 in the paper illustrate the power transfer demo. Picture this. They set up the tabletop scenario. The battery-operated hub device is placed on a person's left arm, ready to inject power. An off-chip inductor is connected in series at the transmitter, forming that series resonant circuit.
Okay.
Then, on the receiving side, let's say on the person's right hand, they connect a test circuit representing the NORD. This circuit includes an inductor, capacitor, and resistor, an LCR network, that can be tuned to precisely match the impedance of the body channel, ensuring maximum power transfer is received. A portable oscilloscope is connected across the resistor to measure the voltage.
So you can literally see the power arriving.
Yes, you can visibly see the voltage waveform on the oscilloscope, demonstrating the reception of power at the NOR side transferred directly through the person's body. The demo also shows the MRPT in action. That initial brief, maybe 2-millisecond scan phase, where the hubby tweaks frequencies to detect resonance. Then it locks onto that frequency and starts transmitting the sustained power.
And does the MRPT handle movement?
That's the key test, right? They demonstrated that when the person moves, say, stretches their arm or changes posture, the body channel characteristics change. This can cause variations in signal loss, sometimes up to 8 decibels, which is quite significant.
Would that normally kill the connection?
Without MRPT, it absolutely could degrade performance severely or even break the link. But the demonstration shows the automatic resonance frequency tracking loop kicking in. It detects the shift caused by the changing return path capacitance or body shadowing and dynamically adjusts the hub's transmission frequency in real time. This nullifies the effect of the movement, maintaining the high efficiency and stable power delivery. The power doesn't drop out just because you moved your arm.
That is seriously impressive. Real-time adaptation. What about seeing data communication?
For data, Figure 18 shows the time domain waveforms, like looking at the signals on an oscilloscope screen. You can see the original transmitted baseband signal, the raw digital data pattern, like Azusan ones, generated by the hubby. Then you see the received on-off keyed signal after it has traveled through the body channel to the node. You can see the carrier turning on and off. And finally, you see the demodulated output at the node, the recovered, clean digital data stream.
Proof that gets through intact.
Exactly. They show this working reliably at a 20 kilobps data rate, with the carrier frequency automatically set by MRPT to the detected resonance point, which was around 1 megahertz in their example. It clearly demonstrates the system successfully encoding information, sending it securely and efficiently through the body, and accurately decoding it at the other end.
Okay, the whole system works, adapts, delivers power, sends data. Incredible. One last technical point. You mentioned the buffers use 90% of the transmit power. Where does the rest of that precious energy go when the hub is transmitting? What's the breakdown?
Yeah, understanding the power distribution is crucial for knowing where future optimizations might come from. Figure 19 provides that clear power breakdown for the hub transmitter. When it's operating at its maximum 1.2-volt supply and delivering that peak 650 microwatts of power into the body, almost 99.9% of that power is consumed by the driving buffer itself.
99.9%. Just the buffer.
Just the buffer. It really underscores how incredibly challenging and energy-intensive it is to drive the capacitive load of the human body effectively at these frequencies. It highlights why their optimized buffer design, with those carefully staged inverters, was so absolutely critical. Even tiny inefficiencies there would have a massive impact.
Makes sense. What about the rest?
Well, despite that huge consumption by the buffer, the design itself is very clean. The paper notes it has a remarkably low leakage power of only 1.1% when idle, indicating good circuit design. And in stark contrast to the buffer, the digital parts, the synthesizable control unit, the brain, and the adaptive clock generator, the heartbeat, consume only about 0.3 microwatts on average.
Wow. So the digital logic is super efficient.
Extraordinarily efficient. This detailed breakdown tells researchers exactly where the energy is going. Future work could focus intensely on further optimizing those power buffers, as even small gains there would significantly impact the overall system efficiency. But the digital control and timing are already incredibly lean. Hashtag outro out.
So we've taken a really deep dive today into this electroquasistatic resonant human body communication, or EQS-Res HPC. It's a truly ingenious system, isn't it?
Right.
Leveraging your own body, your biology, for both reliable power delivery and secure data transfer.
It really is remarkable.
We've seen how series resonance supercharges that power transfer, getting that Q to the fourth boost to help keep devices always on, and how parallel resonance optimizes the data communication, making signals crystal clear with minimal power drain thanks to that Q-cubed foam improvement. And tying it all together is that brilliant maximum resonant power tracking mechanism, the MRPT, constantly listening and adapting to keep the system perfectly tuned to your ever-changing body and environment.
And this groundbreaking work coming out of Purdue, it really is a fundamental, maybe even monumental step towards that Internet of Bodies vision we talked about.
Yeah.
It enables truly batteryless perpetual operation for wearables across the entire body. And it achieves these just unprecedented efficiency gains, remember? Over 100 times more efficient, more than 10 times more power for those long body channels compared to the previous best methods.
Huge numbers.
They are. This isn't just some incremental improvement. It feels like a genuine leap. It makes that vision, the one where you never have to charge your wearable devices again, feel like a real, tangible, and highly efficient possibility. It brings us so much closer to a future where technology is truly invisible and just seamlessly integrated into our daily lives.
It really does. And, this raises a pretty profound question for all of us to consider, doesn't it? As our devices become intrinsically linked to our bodies, not just sitting on them, but powered by them, communicating through them, how might this fundamentally change our relationship with technology? And what new possibilities, what new applications we haven't even dreamed of yet might emerge? But also, perhaps, what new questions about privacy, about security, about identity, maybe even about the very definition of self, will arise when those lines between our biology and our gadgets truly start to blur.
It's a fascinating and maybe slightly unnerving future to contemplate.
It definitely is. A future that seems to be rapidly approaching, and research like this is undeniably opening the door.